Hi everyone, welcome once more to this YouTube channel, Best Science Brain YouTube channel, where you learn chemistry, general chemistry, and other applied sciences. Today, we are looking at stoichiometry of reactions, but we are going further to treat excess and limiting reagents. If you are not subscribed to the channel, you move on to the channel's name, Best Science Brain. Under the channel's name, you have the subscription icon. Tap on the icon only once and get subscribed to be seeing our tutorial videos in this channel. So sometimes in chemical reactions, reactants are introduced in different quantities. The question is, which of the reactants is considered to be in excess and which of them is considered to be limiting? So reagents are nothing but reactants or chemical substances that are involved in chemical reaction. So reagents also mean reactants. So we have the in a chemical reaction between two substances. The substance whose amount is completely used up is known as the limiting reagent. So during chemical reaction between two substances, the substance that is used up completely and whose amount does not remain at the end of the reaction is called the limiting reagent. While a substance whose amount is not completely used up is known as the excess reagent. For instance, if I introduce 100 grams of A into the reaction vessel and then introduce 50 grams of B in the same reaction vessel, if 100 grams of A was completely used up, that means at the end of the reaction, the amount of A is exhausted, nothing is left over. But out of the 50 grams of B I introduced, let's assume that 30 grams was used up. What it means at the end of the reaction, I'll now have 50 minus 30, which is 20 grams of B remaining. Now B is now the excess reagent because we have surplus of B at the end of the reaction, while A that is completely used up is the limiting reagent. The word limiting means insufficient. So the following should be a criteria for a reactant or a reagent to be limiting reagent. So how do you know that a reactant is a limiting reagent? The initial amount, that amount could be mass or mole. So you have M subscript I. That M is mass, while that I represents initial. Or the initial mole, N subscript, small n subscript I, of the substance introduced into the reaction vessel should be less than the calculated mass, calculated reacting mass or mole. So where MR stands for reacting mass and NR stands for reacting moles. So for example, if I introduce 80 grams of a substance into the reaction vessel and assuming that 100 grams of the same substance required for the reaction, that means the 80 gram I introduced is not enough for the reaction since I need 100 grams. So the initial mass Mi is 80 grams, while the reacting mass required is 100 grams. That means that substance now becomes limiting, not insufficient for the reaction. So let's continue. Conversely, the following should be a criteria for a reactant to be an SS reagent. So for a reactant to be an SS, it means the initial mass Mi or mole Ni of the substance introduced into the reaction vessel should be greater than the calculated reacting mass Mr or mole Nr. So for a substance to be in excess, let's assume that I introduce 70 grams of a substance into the reaction vessel and perhaps only 50 grams required for the reaction. So the leftover becomes 70 minus 50, that is 20 grams. So if the initial mass or mole introduced is more than what you expect to react, that means the substance is now in excess. Okay, having done that, we'll now look at this illustration here. So this illustration will give us a better understanding of excess and limiting reagent. Let us use the diagram below to further explain the meaning of limiting and excess reagent. So let that vessel represent a reaction vessel. And we see reactant A introduced on the left, from the left-hand side. And the mass of A, Mi, introduced mass of A is 15 grams. We see reactant B introduced from the right-hand side of the vessel. And the mass of B introduced is 18.2 grams. That's the initial masses. The reaction that occurs is A molecule plus B molecule giving us 2 moles of AB. Then in the balls or yellow balls there, Mr, which means the reacting mass of A is 17.2 grams. Then MrB, the reacting mass of B is 16.5 grams. Question is this: which of these substances is now said to be in excess? If you consider the initial mass of A is 15 grams, then the mass will introduce. The reacting mass of A is 17.2 grams. There's no how you introduce 15 grams of A and you expect 17.2 grams to react. That means what you expect, the mass of A that is going to react is more than what is introduced. That means we need 17.2 grams for the reaction, and what was introduced is 15 grams. That means A is insufficient for the reaction. That means the whole 15 grams will be used up in the reaction. I will need extra 17.2 minus 15, need extra 2.2 grams of A to be added. So A is not sufficient for the reaction. That means A is called the limiting reagent or insufficient reagent. Then let's look at B. The mass of B introduced is 18.2 grams, and the mass of B, Mr for B, required for reaction is 16.5. So we introduce 18.2 grams and 16.5 grams of B reacted. That means we're going to have surplus of B remaining. That's 18.2 minus 16.5. So B is now the excess reagent. So for a substance to be in excess, you have to compare the initial mass to the reacting mass. If what you introduce is higher than what's going to react, that means that substance will be in excess, like in the case of B now. So we introduce 18.2. Out of 18.2, 16.5 will react. That means I have about 1.7 grams of B remaining. That means B is in excess. But A is insufficient. We introduce 15 grams of A and we need 17.2, which is higher than 15, to react. That means we don't have enough of A for the reaction. That means A is the limiting reagent. So for the excess reagent, Mi for that substance should be more than Mr. For the 18.2 is higher than 16.5. For the limiting reagent, Mi should be less than Mr. Now, in questions or in the stoichiometric questions involving limiting and excess reagent, you'll be provided with the initial amount of A, be it mass of A or moles of A, and the initial amount of B. But the reacting masses of the substances or the reactants, Mr for A or Mr for B, will not be given to you in the equation. You calculate it from the stoichiometric equation. So we'll be given initial masses, but the reacting mass will not be given to us. So let's go to examples now. Let's look at this example. Exercise 1 says 10.0 grams of sodium triosocarbonate 4 or sodium carbonate was treated with 15.0 grams of HCl until effervescence or gas liberation stopped. Determine the I limiting reagent, II excess reagent, III mass of sodium chloride produced. Okay, let's start with solving I and II. From the question, they gave us the mass of sodium carbonate, that the initial mass of sodium carbonate, Mi for sodium carbonate. And we're also given the initial mass of HCl introduced. So let's go to the solution. So since there's a reaction there, we're going to write the balanced equation between sodium carbonate and HCl. You have 1 mole of sodium carbonate reacting with 2 moles of HCl to give us 2 moles of sodium chloride, 1 mole of water, and 1 mole of CO2. So the balanced equation is very necessary since there's a chemical reaction. Then from the equation, the initial mass of the carbonate, sodium carbonate Mi, is 10.0 grams. The initial mass of HCl given to us as 15.0 grams. Now for a solvent to be limiting, or for a limiting reagent, the initial mass should be higher than the reacting mass. And for excess reagent, the initial mass should be higher than the reacting mass. So what we are giving the initial masses, we're going to calculate the reacting masses. So first, we need to calculate the reacting masses of the reactants or reagents before drawing a conclusion. So we now have a table for the calculation of the reacting masses. So we have the first column, Mr, the reacting mass of HCl, and the second column, Mr, reacting mass of sodium carbonate. We work from the balance equation. If you go to the balance equation, condense sodium carbonate to HCl. How many moles of each? You have 1 mole of sodium carbonate to 2 moles of HCl. So we go back. We have 1 mole of sodium carbonate equivalent to 2 moles of HCl. We now convert the moles to masses. And we know that 1 mole of a substance is the molar mass of the substance. So 1 mole of sodium carbonate is what the molar mass, which is calculated or given in the equation. 106 grams of sodium carbonate equal to, and then 1 mole of HCl is also the molar mass. The molar mass of HCl is 36.5. But since we have 2 moles in the equation, we have 36.5 times 2. So we have 106 grams of sodium carbonate equals 73 grams of HCl. Therefore, since we're working with sodium carbonate, therefore 10 gram. 10 gram is the initial mass of the carbonate given to us in the equation. That is it. So therefore, 10 gram of carbonate will now react with 10 times 73 over 106. That gives us 6.89 gram of HCl. So this is the reacting mass of HCl. The mass of HCl is expected to react or expected to be consumed in the reaction, 6.89 gram. So we have to now consider, is HCl a limiting reagent or an excess reagent? The reacting mass is 6.89. The what mass of HCl was introduced? The mass of HCl introduced, you can see there is 15 gram. We introduced 15 gram and 6.89 gram of HCl reacted. That means that HCl is in excess. What you introduce is more than what is going to react. By how much? By 15 minus 6.89 gram. Then let's work on sodium carbonate. Then find the reacting mass of sodium carbonate. The same thing we did here. All we have to do is to swap. Instead of saying 1 mole of sodium carbonate to 2 mole, we can start with HCl. 2 moles of HCl related to 1 mole of sodium carbonate. That is swapping the position of the first statement. 2 moles of HCl, 1 mole of sodium carbonate. Then convert the mole to mass, change the mole to molar mass. So because 1 mole of a compound is equal to the molar mass. So 2 moles is now 2 times 36.5 gram of HCl. The 1 mole of HCl, sodium carbonate is the molar mass. That is 106 gram of sodium carbonate. 73 grams of HCl equivalent to 106 grams of sodium carbonate. Therefore, 15 grams of HCl, since we're working with HCl now, 15 grams of HCl is nothing but the initial mass of HCl given to us in the equation. You can see it there, 15 grams of HCl. So therefore, what will 15 grams of HCl react with? We're going to react with 15 times 106 by proportion over 73. That gives us 21.8 grams of sodium carbonate. So this is the mass of sodium carbonate expected to react. We'll now compare this reacting mass with the initial mass. The initial mass of sodium carbonate is 10 grams. So we introduce 10 grams, and then the reacting mass is more than what you introduced, 21.8. So the mass we introduce is less than what should react. So that means sodium carbonate is insufficient. 10 grams, and then we'll expect 21.8 grams to react, which is impossible from the 10 grams. That means sodium carbonate is limiting, is not sufficient for the reaction. So that is the conclusion. Now we'll go to question number 2, which says we should calculate the mass of sodium chloride produced. That is should be II. Okay, III. Well, identify the limiting reagent III, mass of sodium chloride produced. So how do we go about it? So to find the mass of sodium chloride produced, what do? We'll connect one of the reactants to sodium chloride. Look at the balance equation. You see the question mark is on sodium chloride because that NaC is the unknown substance now. As I normally use the word unknown, the one you're looking for. You connect it to the known. But you know that the mass of sodium carbonate was given to you. The initial mass was given to us as 10 grams. And HCl, the initial mass was given us as 15 grams. But we have to decide to use one reactant and one product. So it's best to use the limiting reagent. The limiting reagent is sodium carbonate, not the excess reagent, not HCl. So connect the limiting reagent to the product because the limiting reagent reacted completely to give you the products, 10 grams of sodium carbonate was totally consumed in the reaction. If I use HCl, I may land at an error. So to be on the safe side, use the limiting reagent. So say in order to calculate the mass of sodium chloride produced, we connect the limiting reagent, the one that's not in excess, sodium carbonate, to sodium chloride in the balance equation. As I can see, the stoichiometric mole ratio is 1 mole of carbonate to 2 moles of sodium chloride. So 1 mole sodium carbonate to 2 moles of sodium chloride, you can see that. So we'll now change the 1 mole of the carbonate, we'll change it to molar mass. We know in chemistry that 1 mole of a substance is same thing as the molecular mass. So 1 mole of carbonate is same thing as the molar, which is 106 grams of carbonate. And then 1 mole of sodium chloride, the molecular mass, which is 58.5 when calculated with atomic masses. So, but there are 2 moles here. Now say 58.5 times 2. That gives us 117 grams of sodium chloride. Therefore, 10 grams of sodium carbonate, with the mass of carbonate introduced initially, will now give us 10 times 117 over 106 by proportion. That will give us 11.0 grams of sodium chloride. Question IV says we should find the volume of CO2 gas liberated. You see, that's why the question mark is on CO2. We still connect the limiting reagent. Don't use the SS reagent. Although that's the way I will use the SS reagent, I will still get the correct answer. But to be on the safe side, use the limiting reagent because the limiting reagent reacted completely to give you the product. So we'll connect sodium carbonate again to CO2. The mole ratio is 1 mole of carbonate to 1 mole of CO2. So it reads, in order to calculate the volume of CO2 evolved, we connect the limiting reagent, sodium carbonate, to CO2 in the balance equation. So we now have 1 mole of sodium carbonate to give us 1 mole of CO2. And 1 mole of a compound, as I say, is the molar mass. So replace that 1 mole with 106 grams of sodium carbonate. Then since we're looking for volume of CO2, we don't have to use the molar mass of CO2. We're not looking for mass. We'll now change CO2, 1 mole is a gas, to 22.4 because 1 mole of a gas occupies a constant volume, 22.4 dN cube at STP. So 106 grams of sodium carbonate gave us 22.4 dN cube, changing the 1 mole of CO2 to molar volume to 2.4 dN cube at STP. Therefore, 10 grams, which is the mass of the carbonate, which was introduced, will now give us 10 times 2.4 over 106, and that will give us 2.11 dN cube of CO2. So it's a note. The limiting reagent sodium carbonate was used in the calculations in question III and IV because all of this quantity reacted to give us the product. So that why we did not use the SS reagent to calculate the products, as I explained before. We now look at exercise 2. Let's say in the laboratory preparation of hydrogen gas, a student added 5 grams of zinc into a conical flask containing 250 cm cube of 0.1 mole per dA cube HCl. Write a balanced equation for the reaction. Say 3 ways in which the rate of reaction above could be increased. Then I. Determine the limiting reagent and SS reagent. IV. Determine the mass of unreacted reagent. Then V. Determine the mass of hydrogen gas evolved at STP. And they give out atomic mass of zinc. Zinc is element 65, a metal. Then the molar mass of HCl is given to us directly at 36.5. The atomic mass of hydrogen is 1. So the first question is write the balance equation. So this is the equation between zinc and HCl. Zinc being more electropositive than hydrogen will display hydrogen from acid. So you have zinc chloride and the hydrogen gas evolve. So you have a balance equation. The II says what factors will increase the rate of reaction. So to increase the rate of reaction, we can increase the concentration of the acid HCl, or we can grind the zinc into dust. That is, increase the surface area of zinc. And then number 3, you can also increase the temperature of the reaction system by heating the mixture. So these factors can increase the rate of chemical reaction. Now we'll now go to triple I, where we're asked to determine the SS and limiting reagent. The mass of zinc introduced from the equation is 5.0 grams. We convert this mass to mole, initial mole, giving us zinc. Zinc is a monatomic element in metal. We use mass over atomic mass to find the number of moles. Divide 5 by 65 to find the number of moles of zinc, which is a 0.07669 mole of zinc. So you can work with mass, you can still work with mole. Then for HCl, the other reagent or reactant, they gave us the concentration 0.1 mole per dn cube and the volume 250 cm cube in the equation. We can still calculate this number of mole, initial mole, using the formula that connects concentration and mole, CV, over 1000, because the volume is in cm cube. So 1000 there is to convert the cm cube to dn cube. Substitution, C is 0.1, V is 250 over 1000. So we'll now have 0.0250 mole of HCl. So this is the initial mole of HCl. What is the initial mole of zinc? And remember that for the SS reagent, the initial mole should be higher than the reacting mole. For the limiting reagent, the initial mole should be less than the reacting mole. The same thing that we said with respect to masses. So we'll now calculate the reacting NR, reacting mole of zinc, or the expected reacting mole of zinc, as the case may be, the reacting mole of HCl, or the expected reacting mole of HCl. We work from the balance equation. We'll connect HCl to zinc. Look at the balance equation. We'll have 2 moles of HCl to 1 mole of zinc. So from the balance equation, 2 moles of HCl reacted with 1 mole of zinc. Therefore, how many moles of HCl do we have in the reaction that was introduced? That is 0.025 calculated before from the formula CV 1000. Therefore, 0.025 mole of HCl react with 0.0525 times 1 over 2 by proportion. We now have 0.0125 mole of zinc. So the reacting mole of zinc is 0.0125 mole. Is zinc in excess or is zinc limiting? Let's find out. If zinc is in excess, the initial mole should be higher than what is going to react. So what amount of zinc was introduced? 0.0769 mole. What amount of zinc reacted? 0.0125. So 0.0769 is higher than 0.0125. That means zinc is in excess, because what you introduce is less than what's going to react. So going to have surplus at the end of the day. Then we'll go to HCl. For the balance equation, the same thing. We just same statement swapped. 1 mole of zinc equivalent to 2 moles of HCl. Therefore, we are working with zinc. The number of moles of zinc is calculated 0.0769 moles. We react with 0.0769 times 2. And that will give us 0.154 mole of HCl. So is HCl in excess? Let's find out. What amount of HCl was introduced? We introduced 0.025. What amount will react? The amount of HCl that will react is 0.154. So what you introduce is less than what's supposed to react. That means HCl is not enough. HCl is limiting. Okay, we'll now go ahead and say hydrochloric acid is limiting, as I said, because the initial amount Ni is less than Nr. 0.025 mole of HCl was introduced, but 0.154 mole of that is required for reaction. So that means you don't have enough acid, because what you introduce is less than what is supposed to react. Hence, that is insufficient or limiting. Zinc is in excess. Ni is higher than Nr. Why? We introduced 0.0769 mole of zinc, was realized in Ni, and only small amount of it, a fragment of it, 0.0125 mole of zinc actually reacted. So what you introduced for zinc is higher than what's going to react. That means zinc is actually in excess. Then number IV, we're looking for the mass of unreacted zinc. First of all, we'll find the number of moles of unreacted zinc. How to find it? We'll subtract Nr from Ni. Number of moles of zinc introduced is 0.0769. Number of moles of zinc that reacted is 0.0125. So when you subtract, you have the number of moles of zinc that did not react. That gives us 0.0644 mole of zinc unreacted. So to find the mass of unreacted zinc, we convert that mole to mass. Zinc is a monatomic element, so mass is mole times atomic mass. So don't use the molecular mass or molar mass for zinc because zinc is monatomic. It's not a compound or a molecule. So convert mass to mole, multiply 0. The mass unreacted by the atoms of zinc is 0.0644 times 65. We now have 4.19 grams of zinc unreacted. Okay, the next question says we should find the mass of hydrogen gas liberated. Mass of hydrogen gas liberated in the reaction. We have the balance equation. We're looking for hydrogen. That's why the question mark is on hydrogen. We sometimes do connect to hydrogen. Connect HCl. Because HCl the emitting, as I explained in the previous question, you connect the emitting reagent to what you're looking for to the product. Then in order to calculate the mass of hydrogen gas evolved, we connect the emitting reagent HCl to hydrogen in the balance equation. You see that 2 moles of HCl equivalent to 1 mole of hydrogen gas. That is stoichiometric ratio. So 2 moles of HCl equivalent to 1 mole of hydrogen gas. Then we can now convert the mole to mass, or we can say work as we have there. 2 moles of HCl gave us 1 mole of hydrogen gas. 2 moles of HCl gave us 2 grams of hydrogen gas. How do we get the 2 grams? The 2 grams of hydrogen gas is the molar mass. The molecular mass of hydrogen gas obtained above. 2 times 1, 2 grams per mole. And you know that 1 mole of a compound is equal to the molar mass. So since we're looking for mass of hydrogen gas, not volume, we change the mole of hydrogen gas to mass. So 2 moles of HCl gave us 2 grams of hydrogen gas. Therefore, the reactive mole of the limiting reagent, that is 0.025 mole of HCl, will now give us 0.025 times 2 over 2 by proportion. Or that will still give you the same 0.025 gram of hydrogen gas. Exercise 3 says 4.00 gram of ammonia and 14.0 gram of fluorine are allowed to produce dinitrogen tetrafluoride N2F4 as shown below. We have the equation between ammonia and fluorine. So giving us dinitrogen tetrafluoride and then hydrogen fluoride. We ask which is the limiting reagent. Which reagent is in excess and by how much? How many grams of dinitrogen tetrafluoride and hydrogen fluoride are produced? So this is we are just applying the same thing that we have done before, the same solution. So we now get the equation down. The initial mass of ammonia, that's the Mi for ammonia, in the equation is 4 grams. That's the mass of ammonia introduced for reaction. The initial mass of fluorine is 14 grams. And then we know that for limiting reagent, the initial mass should be less than the reacting mass or the expected reacting mass. And for excess reagent, the initial mass should be higher than the reacting mass. So we have been given the initial masses in the equation. We have to calculate the reacting masses. So firstly, we need to calculate the reacting masses of the reactants, or you can say the reagents, before drawing conclusion. First of all, let us find the molar mass of the reactants. The molecular mass of ammonia is calculated 14 plus 3 times 1. 14 atomic mass of nitrogen and 1 atomic mass of hydrogen times 3 equals to 3 atoms. That gives you 17 grams per mole for ammonia. And for fluorine, being a molecule, the molecular mass is 2 times 19. The atomic mass of fluorine atom is 19. And there are 2 atoms that give you 38 grams per mole. We'll now calculate in the table the reacting mass of fluorine and the reacting mass for ammonia. From the balance equation, you go to the equation, you see that the connection is 2 moles of ammonia to 5 moles of fluorine. For the balance equation, 2 moles of ammonia reacted with 5 moles of fluorine. Then we know that 1 mole of a compound is equal to the molar mass. So 2 moles becomes 2 times 17 because the molar mass of ammonia is 17. 2 times 17, while the molar mass of fluorine is 38. 5 times 38. So we now have 34 grams of ammonia. 2 times 38 is 34. Equivalent to 190 grams of fluorine. 5 times 38 is 190. Therefore, 4 grams of ammonia, which is the initial mass of ammonia given to you in the equation, will give you 4 times 190 over 34 by proportion. We now have 22.4 grams of fluorine. So this is the reacting mass of fluorine, 22.4 grams of fluorine. So we now decide if fluorine in excess, we look at the initial mass of fluorine is 14 grams introduced. Then what mass of fluorine reacted? The mass of fluorine that reacted is 22.4 grams. So the mass of fluorine that reacted is more than what was introduced. You introduced 14 grams, and the 2.4 grams is expected to react. That means the 14 grams of fluorine introduced is not enough for the reaction. So that means that fluorine gas is limiting, insufficient for the reaction. So fluorine is limiting because Mi is less than Mr. Now, we work on ammonia. For the balance equation, the same thing, just swap the first statement. 5 moles of fluorine now to 2 moles of ammonia. Convert the moles to molar masses, that is 5 moles is 5 times the molar mass. Since molar mass is the mass of 1 mole, so 5 times 38 is 190 grams of fluorine. Then convert 2 moles of ammonia to mass, 2 times the molar mass, 34 grams of ammonia. Therefore, 14 grams of fluorine. 14 grams is the mass of fluorine that was initially introduced. Since we're working with fluorine now, when I give up 14 times 34 over 190, give us 2.151 grams of ammonia. So the reacting mass of ammonia is 2.51 grams. Now, what the initial mass of ammonia? The initial mass of ammonia introduced is 4 grams. So introduce 4 grams of ammonia, and then 2.51 grams of ammonia is reacting. That means ammonia is in excess. Because when you introduce 4 grams is higher than what is reacting, we're going to have extra or surplus remaining for ammonia. So the solution reads, the limiting reagent is fluorine. This is because the initial mass is less than the reacting mass. 14 grams of the reagent will introduce, but 22.4 grams of the substance is expected to react. Hence, the quantity of fluorine introduced is insufficient for the reaction. So you introduce 14 grams. 22.4 grams is expected to react. That means you do not introduce enough fluorine. So fluorine is insufficient. Then, the reagent in excess is ammonia. This is because the initial mass is higher than the reacting mass. 4 grams of ammonia was introduced, but 2.51 grams of ammonia reacted. So 4 grams out of 4 grams, 2.51 reacted. That ammonia is in excess, is more than sufficient for the reaction. And mass of unreacted ammonia, we have to find the mass of unreacted ammonia, would now become the Mi for ammonia minus Mr for ammonia. That is 4 minus 2.51, giving us 1.49 grams of ammonia unreacted. Question C says we should find the mass of the products obtained. As we used to do, or as I explained before, to find the mass of the product, you connect the limiting reagent to the products one by one. So we say in order to calculate the masses of the products, we connect the limiting reagent, fluorine, the one that is not enough, since all its mass reacted to the product in each case. So since we're looking for the mass of the 2 products, let's start with one of them. Let's start with dinitrogen tetrafluoride. So the initial mass of fluorine is 14 grams. That's the insufficient reagent. Then the molar mass of fluorine is 2 times 19, that is 38 grams per mole. The molar mass of dinitrogen tetroxide is going to be 2 times 14 for nitrogen plus 4 times 19 for fluorine. That gives us 104 grams per mole. So from the balance equation, we see that the connection is 5 moles of fluorine to 1 mole of dinitrogen tetrafluoride. So when I say connecting fluorine, that the known to the unknown, N2F4, the balance equation will now have 5 moles of fluorine to 1 mole of N2F4. We'll convert the mole to mass. You know that the 1 mole of the compound is the molar mass. So 5 moles becomes 5 times 38, giving us 190 grams. The 1 mole of that compound, N2F4, is 104 grams. So bring 104 grams down. So 190 grams of fluorine is giving us 104 grams of the compound. Therefore, 14 grams of fluorine, which is the mass of the limiting reagent, 14 grams of fluorine will now give us 14 times 104 all over 190. And that will give us 7.66 grams of dinitrogen tetrafluoride produced. Then the next is to find the mass of the other product, which is hydrogen fluoride. It says similarly, we calculate the mass of hydrogen fluoride produced using also the same limiting reagent, because its mass was depleted in the reaction. We still connect the same fluorine to hydrogen fluoride. Now, the unknown is hydrogen fluoride. So the initial mass of fluorine is also the same 14.0 grams, given the equation. The molecular mass of fluorine have been done several times, that is 38 grams per mole. We'll now find the molecular mass of HF, which is 1, so mass of hydrogen is 1, plus 19 for fluorine, giving us 20 grams per mole. We'll now connect the two of them, fluorine to HF, in the balance equation. We'll see that the stoichiometric ratio is 5 moles of fluorine to 6 moles of HF. So connecting fluorine to HF in the balance equation, we'll now have 5 moles of fluorine to 6 moles of hydrogen fluoride. We'll convert the moles to masses. So 5 moles of fluorine is 5 times the molar mass, 38 grams of fluorine. 6 moles of HF is 6 times the molar mass, 6 times 20. So we now have 190 grams of fluorine to 120 grams of HCl. Therefore, 14 grams of fluorine given to you in the equation will now give you 14 times 120 over 190. That will give us 8.84 grams of hydrogen fluoride produced. So you see, when you are solving problems on limiting and excess reagent, the initial masses or moles of the substances that are reacting, the reagents, the reactants given to you, you have to calculate the reacting masses using the stoichiometric ratios from the balance equation, find the reacting masses. When you have done that, then for each of the reactants, compare the initial mass to the reacting mass. If the initial mass is higher than the reacting mass, that means the substance is in excess. Introduce 20 grams, for instance, and 15 grams will react. That means you're going to have extra 5 grams remaining. But if the initial mass or mole is less than the expected reacting mass, that means the substance is insufficient or limiting. Introduce 5 grams and then you expect 10 grams to react. It's not possible. You introduce 5 grams and you need 10 grams to react. That means what you introduce is not sufficient or is a limiting reagent. So we'll now go to the next aspect, analysis of a mixture. You know, in chemistry, a mixture is a substance formed when 2 or more substances are physically combined. A mixture has no chemical formula in chemistry, but the components that make up a mixture have their individual formulas, but you cannot represent a mixture with a chemical formula. For instance, when you pour salt inside water, salt is a compound, water is a compound. When you mix them together, you form salt water. So salt has its own formula, NaCl. Water has its own formula, H2O, but there's no formula that represents both salt and water together, no, because the substances are physically combined and can be separated by physical means. So a mixture has no formula. In chemical reactions involving a mixture, so most at times when you have a chemical reaction involving a mixture or 2 substances that make up the mixture, it is only one of the substances that will react with the second reagent, while the other one will remain unreacted. So let's look at this statement. We say in a mixture, the constituents, which could be compounds, elements, or both. So in a mixture, the constituent, like I use salt and water, you can see have sand and zinc. Zinc is a metal, while sand is silicon foil, is a compound. It's also a mixture. So the concept of a mixture can be compounds mixed together, can be elements mixed together, like zinc and sulfur. Can also be element and compound, like sand and zinc. So say in a mixture, the constituents, which could be compounds, elements, or both, are not chemically combined. Hence, a mixture cannot be represented using a chemical formula. You see the reason for that? Even though its components have their individual chemical formulas. In a chemical reaction involving a mixture and another reagent, only one of the components of the mixture would react with a given reagent, and it is this component that will be used in writing the balance equation. So let's take an example to understand this. Exercise 1 says 2.0 gram of a mixture of common salt and sodium triiodocarbonate 4. We are treated with 250 cm cube of 0.1 molar HCl. So you have a mixture of common salt and sodium carbonate reacting with HCl. Okay, let's continue. Write a balance equation for the reaction. Calculate the percentage by mass of sodium chloride in the mixture. And the molar mass of sodium chloride given to us already as 58.5 gram per mole. The molar mass of sodium carbonate given us as 106 gram per mole. Solution: to write the equation, that way we'll have issue now. The mixture has no chemical formula. It is only one of the components of the mixture that will react with the acid. So we have two components, sodium chloride and sodium carbonate. So which of them will react with the acid? Sodium chloride, or otherwise called common salt, will not react with HCl. Why? Because it's a normal salt of the acid of HCl. Both substances contain the same anion. Anion means negative ion. So both sodium chloride and HCl contain chloride ion and chloride ion. So they cannot react together. Hence, the equation for the reaction is given as, so the component that react with in the mixture that react with the acid is sodium carbonate, not sodium chloride. So that is the reaction. HCl plus sodium carbonate, not plus sodium chloride, because sodium chloride will not react with acid, giving us sodium chloride, water, and CO2. Equation is balanced. Looking at it. So, having done that, from the equation, the volume of HCl given to us as 250 cm cube. The concentration of HCl is 0.1 mole per dm cube. So we have the volume of the acid and the acid concentration. With these two values, C and V, we can find the number of moles of the acid using CV over 1000. The 1000 there is convert the volume to dm cube. Making substitution, we have 0.1 times 250 over 1000. And that will give us 0.0250 mole of HCl reacting or participating in the reaction. Okay, having done that, we need to calculate the mass of sodium carbonate that reacted. Remember, the question is we should find the percentage of sodium chloride in the mixture. We have to first of all find the mass of sodium carbonate that reacted, and that will represent the mass of sodium carbonate in the mixture. So we need to calculate the mass of sodium carbonate that reacted with HCl. This represents the mass of sodium carbonate in the mixture. So we'll go to the balance equation and be able to connect HCl to sodium carbonate. You see the equation, 2 moles of HCl to 1 mole of sodium carbonate. So that we can calculate the mass of sodium carbonate that reacted, and that will represent the mass of the carbonate in the mixture. So, connecting, you look at it, we have 2 moles of HCl. The two were made bold. HCl is the known, while sodium carbonate is the unknown, the one we're looking for. So 2 moles of HCl reacted with 1 mole of sodium carbonate from the balance equation. We can convert those moles to masses. Okay, let's find the number of moles. Okay, we can still work with mole concept. 2 moles of HCl is combined with, let's push it to the right side. 2 moles of HCl reacted with 1 mole of carbonate. Therefore, 0.025 mole of HCl. This 0.025 have been calculated before as the reacting mole of HCl using that formula CV over 1000. So 0.025 mole of HCl will react with 0.025 times 1 over 2. We now have 0.125 mole of sodium carbonate that reacted, and that represents the mole of carbonate in the mixture. We have to convert this mole now to mass. So mass of carbonate in the mixture is now again as the formula mole times molar mass. Sodium carbonate is a compound, so we calculate the mass using mole times molar mass. And in the equation, the molar mass of carbonate was given to us as 106. Make substitution, the mole of carbonate is 0.0125 times molar mass 106, and that gives us 1.33 grams of sodium carbonate in the mixture. So this is the mass of carbonate that reacted, and that's the mass of carbonate in the mixture. Now to find the mass of salt, common salt in the mixture, what do? We will now become mass of mixture minus mass of sodium carbonate that reacted. Mass of mixture is given to you in the equation as 2 grams minus 1.33 grams, which is the mass of the carbonate that reacted, and that's the mass of carbonate in the mixture. So remaining will now become the mass of sodium chloride, which is 0.670 grams of sodium chloride. So percentage of sodium chloride in the mixture is going to be mass of sodium chloride all over mass of mixture times 100 over 1. Mass of sodium chloride is 0.670 gram. That gives us 0.67 gram over 2. That's the mass of the mixture in the equation times 100. And that will give us 33.5% of sodium chloride in the mixture. So that is it. So go to exercise 2 that says 12.6 grams of a mixture of zinc carbonate and zinc oxide were strongly heated. 4.8 grams of zinc oxide was obtained from zinc carbonate. What is the weight percentage of zinc carbonate in the mixture? So the mixture consists of zinc carbonate and zinc oxide, and the mass of the mixture is 12.6 grams. On heating the mixture, 4.82 gram of zinc oxide was obtained. If you look at the equation, zinc oxide was mentioned 2 times. There's zinc oxide in the mixture, that is in the 12.6 gram of the mixture. Then there's also another 4.82 grams of zinc oxide obtained on heating the mixture. Now, the mass of zinc oxide obtained as residue, that is 4.82 grams, is different from the zinc oxide that is present in the mixture. So the 4.82 gram of zinc oxide was obtained by decomposing the zinc carbonate in the mixture, which is different from the zinc oxide that is already present in the mixture. So when you heat a mixture of zinc carbonate and zinc oxide, one of the compounds will decompose, and the other one that decompose will be the zinc carbonate, while the zinc oxide in the mixture will not decompose. So we go to the solution to the equation. First, we write a balanced equation for the decomposition of zinc carbonate. Zinc oxide in the mixture does not undergo thermal decomposition as we mentioned. So in this mixture, only one of the substances undergoes reaction. That is zinc carbonate breaks down to the zinc oxide, which gave up 4.82 grams of zinc oxide and then CO2. We say note the zinc oxide in the above equation obtained from the decomposition of zinc carbonate is different from the zinc oxide present in the mixture. As I said, the zinc oxide in this equation present the 4.82 grams obtained is different from the zinc oxide that is already present in the mixture because that one didn't undergo any reaction or any decomposition. So next, we have to calculate the mass of zinc carbonate that decomposed to give us the 4.82 grams of zinc oxide. So how do we do that? We now go to the equation. Go to the equation. We're looking for the mass of zinc carbonate. That's why the question mark is on zinc carbonate. And then zinc oxide, the two substances were made both. Why is this so? Because they are the substances we are connecting. The zinc carbonate is the unknown substance which we are looking for its mass. And the zinc oxide, the mass produced 4.82 grams was given to us. So mass of zinc oxide produced is 4.82 grams. From the equation, we find the molecular mass of zinc oxide, 65 for zinc plus 16 for oxygen. We have 81 grams per mole. That is the molar mass of zinc oxide. We also find the molar mass of the zinc carbonate, the two compounds consigned. 65 for zinc plus 12 for carbon plus 3 times 16 for oxygen. And that will give us 65 plus 12 plus 48, giving us 125 grams per mole. Then connecting the two substances together, zinc oxide to zinc carbonate, the stoichiometric ratio is 1 mole to 1 mole. We now have 1 mole of zinc oxide equivalent to 1 mole of zinc carbonate. So since 1 mole is equivalent to the molar mass, we now say 81 grams of zinc oxide equivalent to 125 grams of zinc carbonate. Therefore, 4.82 grams of zinc oxide, 4.82 represent the mass of zinc oxide produced in the reaction, will now be equivalent to 4.82 by times 125 over 81 by proportion. That gives us 7.44 grams of zinc carbonate in the mixture. And they represent the mass of zinc carbonate in the mixture, that's 7.44 grams. So this implies that there is 7.44 grams of zinc carbonate in the mixture. So percentage of zinc carbonate in the mixture becomes mass of zinc carbonate over mass of mixture times 100/1. So mass of zinc carbonate obtained from calculation is 7.44, which is the mass of zinc carbonate in the mixture, all over the mass of mixture given to us in the equation as 12.6 times 100/1. And that gives us approximately 59%. We now go to percentage yield. Sometimes in stoichiometric equations, you are asked to find the percentage yield of a substance. During a chemical reaction, we have products produced at the end of reaction. When reactants combine, products are formed. Then, if we're able to gather the products and weigh it by gravimetric analysis using chemical balance, the mass of product obtained is called the actual yield that we weigh after the chemical reaction. But the mass of product we obtain by calculation from the chemical equation is called the theoretical yield. Sometimes the actual yield is less than the theoretical yield. They are not equal to each other due to some technicalities involved in chemical reaction. So we'll now say the quantity of product isolated from a chemical reaction is the theoretical yield. So this is the mass you calculate from a balance equation. It's called the theoretical yield. However, in the laboratory, it's difficult to account for every drop of liquid and every crumb of solid. In addition, the methods used to purify compounds are capable of separating the desired products completely from the reaction mixture. Hence, the actual yield of the compound may be less than the theoretical yield. As I said, the actual yield is the actual mass of the product you obtain when you weigh it, while the theoretical yield is the mass you calculate from a balanced equation. So we want to find the percentage yield. It's going to be actual yield all over theoretical yield times 100 over 1. So let's take a question to illustrate that. Look at that reaction between sodium 3 moles of sodium tetrahydroborate 3 and 4 moles of boron fluoride, giving us sodium tetrafluoroborate 3 and boron hydride. So let's look at the question. It says 18.9 grams of sodium tetrahydroborate 3 NaBH4 was reacted with excess boron 3 fluoride to give 7.50 grams of boron hydride. What the percentage yield of boron hydride? Solution. We'll first calculate the mass of boron. Since we look for the percentage of boron hydride, yes, look at the question. We'll first calculate the mass of boron hydride produced from the stoichiometry reaction. And this mass of boron hydride you're going to calculate is called the theoretical yield. So that is this is the theoretical yield of boron hydride. So this is the equation. If you look at the equation, they gave us the mass of boron tetrahydride, mass of boron tetrahydroborate 3, mass of sodium tetrahydroborate 3 or sodium boron tetrahydride, that is NaBH4. The mass was given to us. If you go to the equation, 18.9 grams. So that why is the known substance is made bold. The unknown is boron hydride. It's also made bold and the question mark is on it. So we'll now start our work. Mass of boron tetrahydride, sodium boron tetrahydride is 18.9 grams. We'll find the molar mass of sodium boron tetrahydride, which is 23. Atoms of sodium is 23. Boron is 11. Hydrogen is 1 multiplied by 4 atoms we have there. That gives us 38 grams per mole. We'll find the molar mass of boron hydride. Boron is 11 times 2 atoms, as we can see there. The hydrogen is 6 times, so give us 28 grams per mole. We're now connecting sodium boron tetrahydride to boron hydride. As you can see, 3 moles of sodium boron tetrahydride gave 2 moles of boron hydride. So you go to the next step. You say connecting NaBH4 to B2H6 in the balance equation. 3 moles of sodium boron tetrahydride gave us 2 moles of boron hydride. And in chemistry, a mole is equal to the molar mass. So 3 moles becomes 3 times 38. That gives us 114 grams of sodium boron tetrahydride. And 2 moles for that to become 2 times the molar mass. 2 times 28 gives us 56 grams of boron hydride. Therefore, 18.9 grams of sodium boron tetrahydride, which is the mass given the equation that was reacted, will now give us 18.9 times 56 over 114. And that will give us 9.28 grams of boron hydride. So this mass produced is called the theoretical yield of boron hydride. So 9.28 grams is the theoretical yield of boron hydride. Percentage yield of the compound is mass of boron hydride actually obtained all over mass of boron hydride theoretically obtained times 100 over 1. And mass actually obtained is given to us in the equation as 7.50 grams in the equation, that way it is. While the mass obtained theoretically is the one we calculated from the equation of reaction, which is 9.28. So now I have 7.5 over 9.28 times 100 over 1. And that gives us 80.8% percentage yield of boron hydride. Look at exercise 2. Exercise 2, have 2 moles of phosphorus reacting with 3 moles of bromine to give us 2 moles of phosphorus 3 bromide. It says 12.7 grams of bromine reacted with excess phosphorus according to the equation below. So they gave us the mass of bromine here. And A says what's the typical yield of phosphorus 3 bromide. And then B says if 10.9 grams of phosphorus 3 bromide was isolated, what the percentage yield of this compound? So this 10.8 gram of the compound that was isolated, 10.9 gram of phosphorus 3 is present the actual yield. So the typical yield is the mass of phosphorus 3 bromide we're going to obtain from calculations using the balance equation. So we'll now go to the solution. A says the typical yield of phosphorus 3 bromide is the mass of the compound calculated from the stoichiometry of the reaction, that is from the balance equation. We connect bromine to phosphorus 3 bromide because the equation gave us the mass of bromine as 12.7 grams, as you can see it. So we find the molar mass of the bromine, which is the known substance. 2 times 80, atomic of bromine is 80 times 2, that gives us 160 grams per mole. We find the molar mass of phosphorus 3 bromide. Phosphorus is 31 plus 3 times 80, since there are 3 atoms of bromine in the compound. That gives us 31 plus 240, 271 grams per mole. Connecting bromine to phosphorus 3 bromide. We now have 3 moles of bromine to 2 moles of phosphorus 3 bromide. Changing the moles to molar mass. The molar mass of bromine is 160, so 3 times 160 of bromine, that gives us 480 grams of bromine. Then 2 moles of phosphorus 3 bromide, 2 times 271, that's the molar mass. That gives us 552 grams of phosphorus 3 bromide, PbR3. Then 12.7 grams of bromine, which is given to you in the equation, that reacted, will now produce 12.7 times 542 over 480. And that gives us 14.3 grams of phosphorus 3 bromide, PbR3. So 14.3 grams, which you calculated from the reaction, is the theoretical yield of phosphorus 3 bromide. So the theoretical yield of this compound is 14.3 grams. Then the actual yield is given in the equation, 10.9 grams. Percentage yield, that is question B now. Percentage yield will now becomes mass of PbR3 actually obtained, that the actual yield, all over mass of PbR3, theoretical obtained, that the theoretical yield, times 100 over 1. So we now have 10.9, which is the actual yield, all over 14.3 times 100 over 1, and that gives us 76.2% as the percentage yield of phosphorus 3 bromide. Okay. So we are come to the end of this lecture. So you subscribe to the channel if you are not subscribed by looking at the channel's name, Best Science Brain, or you search it on YouTube or on Google, Best Science Brain, and then tap on the subscription button or icon under the channel's name, Best Science Brain. Tap and get subscribed for more videos on general chemistry. Thank you.